Good morning, everyone. This is Julie McDonald with Microcom Technologies, and I'd like to thank all of you for attending today's webinar with MetaGeek. Today's host is Joel Crane. He's the technical trainer for MetaGeek, and he'll be presenting today. If anyone has any questions, please feel free to submit them in the question box, and Joel will answer them at the end of today's presentation. Joel, I'm finished for now. Thank you so much for being with us this morning. Please go ahead and take it on over.
Great. Thanks, Julie. Welcome to Spectrum Analysis with Channelizer and WiSpy. Just a little introduction so you know a bit about me and a little bit about MetaGeek. My name is Joel, and I'm the technical trainer at MetaGeek. And we're a small company based out of Boise, Idaho, and we make easy-to-use wireless troubleshooting tools, including Channelizer and the WiSpy. In fact, the WiSpy is made right here in make them with real 100% Idaho-grown potatoes. Like Julie said, if you have any questions, feel free to enter those in the question tool. And at the end, I'm going to hand things back over to Julie, and she's going to go ahead and ask those questions. She'll pick the good questions out of there and ask those. So feel free to ask those throughout the course of the webinar. Now, just a little bit of an agenda so that you know what to expect throughout the course of this webinar. We're going to start out by going over some basics and some fundamentals of Wi-Fi. There are some kind of core concepts that you need to understand about Wi-Fi to really get spectrum analysis at a deep level. So we'll start out with those building blocks, and then we'll work our way up, and we'll do a live demo with Channelizer and the WiSpy, so you can see what it actually looks like and how to actually use it in the real world. So the first thing I want to talk about is the half duplex nature of Wi-Fi. Now, what does half duplex mean? Well, you're probably familiar with full duplex Wi-Fi or full duplex communications in Ethernet. If you've ever stripped back the shielding on an Ethernet cable, if you look inside one Ethernet cable, you'll notice that there's multiple twisted pairs of copper inside that one cable. In fact, there's 4 pairs of copper, and that gives us full duplex connectivity. Full duplex connectivity is kind of like a 2-lane highway. With a 2-lane highway, we can send traffic east and west simultaneously at the exact same time. Wi-Fi, on the other hand, is a lot more like a 1-lane highway. With Wi-Fi, we can only send traffic in one direction at a time. It's also kind of like a human conversation. If you say something and if your friend says something at the exact same time, you can't understand them and they can't understand you. Only one of you can talk at a time. Only one person can talk at a time in a conversation. So what do conversations look like in Wi-Fi? Well, let's say that we've got an access point here. Now, this could be a home router. This could be an enterprise-grade access point. This could be a gateway modem router combination that maybe your internet service provider gave you, whatever it is. Let's say that we've got an access point that needs to send some data to a laptop. The first thing that the access point is going to do is it's going to do a clear channel assessment. It's going to listen to the channel to see if anything is talking. And if it decides that the channel is clear and that nothing is talking, it'll take that opportunity to transmit that data, and it will transmit the data to the laptop. Now, the laptop on the other end, it's going to pull out the magnifying glass. It's going to take a look at that data to make sure that it understood the data. And if it does understand the data, it'll go, yep, check, I understood the data, and it will reply with an acknowledgement. Wi-Fi is this constant process of sending data and receiving an acknowledgement and sending data and receiving an acknowledgement. The important thing to remember here is that only one Wi-Fi device can talk on a channel at a time. Only one device can talk. Now, there's a couple of things that can go wrong here, and one of those is retries. Let's say that our access point performs that clear channel assessment and decides that it's able to transmit some data, and it transmits the data across the air to the laptop. But maybe something else starts to talk at the same time. Maybe another Wi-Fi realize there's a conversation happening. Maybe there's a microwave oven that gets powered on or something like that, and something interrupts that transmission. If that transmission is interrupted, the data will get corrupted before it arrives at the laptop. In this case, the laptop isn't going to understand what it heard, so it's not going to transmit the acknowledgement. So after a few moments, our access point will start going, okay, well, I never heard an acknowledgement from the laptop, so the laptop must not have received the data frame. So the access point will transmit the data again and again and again, and it will continually retransmit the data until finally one of those pieces of data makes it through to the laptop, and the laptop can go, yep, check, I understood the data, and it can reply with an acknowledgement. In this way, Wi-Fi is a lot like my kids. I've got 3 kids at home, and the youngest is 3, and the oldest is 6. And Wi-Fi is a lot like my 3-year-old daughter in this way. My 3-year-old daughter, if she asks me a question, let's say I'm sitting on the couch reading a book or something like that, and let's say that she asks me a question. If I don't give her some kind of acknowledgement, she will ask over and over and over and over and over again until finally it makes it through to me and I give her some kind of acknowledgement. I acknowledge what she said. And if you've ever had kids, or maybe if you've just been around some kids like your nephews or nieces or something like that, or maybe if you've just seen some kids from a distance, you know that kids are a lot like Wi-Fi in this way. They will retransmit over and over and over and over again. But the big important thing to remember here is that on any given channel at any given time, only one Wi-Fi device can talk at a time. And that's a concept that most kids don't understand at all. They don't understand that only one person can talk at a time. So let's back out and take a look at a kind of a broader look at this issue. Instead of looking at just one access point and one client device, let's look at an entire channel. Maybe we've got one access point and we've got 6 client devices on this channel. And let's say that we've got an Android phone here and it's currently transmitting some data. While that Android phone is transmitting, all the other devices on the channel have to be quiet and wait for their turn to talk. Remember, on any given channel at any given time, only one device can talk. One device talks on a channel. And this includes neighboring access points as well. If there is a neighboring access point, oh, I forgot to snooze my notifications for my chat application. Let me get rid of that really quick. All right, problem solved. If we've got maybe a neighboring access point as well, like let's say that there's a neighbor over here and they've got an access point and they're on the same channel and they've got a few iPads and a few laptops and maybe like a Roku and a few various devices. All of these devices also have to take turns talking if they're within range. Only one device can talk at a time, whether it belongs to your network or not. If it's on the same channel, we've got to take turns talking, and that's just how things work with Wi-Fi. Now, slow devices can also be a problem as well. Slower devices consume more time on the channel. Basically, it works like this. Let's say that we've got an Android phone, and it's having a conversation, a back and forth conversation with this access point, and since they're pretty close together, it's able to use a nice, fast data rate, like maybe 54 megabits per second. It's a nice, quick data rate. Whereas we've got this other Android device here, it's on the very edge of the coverage cell. It's on the fringes of the coverage cell. So it's had to slow down and use a very slow data rate, like 1 megabit per second. In this scenario, the device that's talking at 54 megabits per second is going to talk 54 times faster. It's going to use 54 times less time on the air. It's going to get on the air and get off the air very, very quickly. Whereas this 1 megabit device is going to talk very, very slowly. It's going to get on the air and slowly say what it needs to say before finally being done. This 1 megabit device is kind of like the slow kid in the back of the classroom. Do you know who I'm talking about? That guy in the back of the classroom? That person that raises their hand and says, teach, I had a question about this particular topic, and you're like, come on, man, just spit it out. Just ask your question. Just say what you need to say so we can move on with the class, right? You know who I'm talking about. You've experienced that, I'm sure. That's exactly what a 1 megabit per second device or a slow device on a network does. So we want to design our networks to work quickly and efficiently. We want devices to get on the air and get off the air very, very quickly, because remember, only one device talks on a channel at a time. Now, what we're here to discuss today is non-Wi-Fi interference. That's what we're going to focus on for the majority of this webinar. And non-Wi-Fi devices, they also need time to talk. For example, an old microwave oven. If the microwave oven doesn't have very good shielding, maybe the door has gotten bent a little bit so it doesn't seal around the door as good as it used to. Maybe the shielding's broken down. Maybe it's just a noisy, cheapo microwave. A microwave oven works by cooking food at 2.4 gigahertz, which is one of the frequency bands that Wi-Fi uses. And if it leaks out any activity at all, any interference, that will directly interfere with our Wi-Fi devices. It will essentially spew out garbage onto the channels that our Wi-Fi devices are on. And Wi-Fi devices know that only one device can talk on a channel at a time. So if they see interference, what are they going to do? They're going to simply back off and be quiet and wait for their turn to talk. They're just going to stop and wait. Now, if the microwave is kind of distant, maybe all it does is raise the noise in the background a little bit. Maybe it just raises the background noise. Well, in that case, our devices are going to have to drop down to lower data rates to make sure that the access point can hear them. And the access point's probably going to do the same thing. It's probably going to drop down to a lower data rate to make sure the client devices can hear it. So a microwave oven will either cause all of our Wi-Fi devices to simply back off and be quiet the whole time it's running, or it'll cause them all to at least slow down to a slower, more understandable, a more robust data rate, which is going to cause congestion on our network and slow things down. And that's something that we want to avoid a lot. And Wi-Fi interference comes in all kinds of different forms. Microwave ovens are just one of the classic examples. Other great examples are 2.4 gigahertz cordless phones, wireless video cameras, baby monitors, Bluetooth devices, Xbox 360 controllers. The list of non-Wi-Fi devices that work in the 2.4 and to some degree the 5 gigahertz bands goes on and on and on and on. They can be really, really problematic. Now, speaking of the 2.4 and 5 gigahertz bands, I want to make a quick comparison between these two. Now, we're not going to go real in depth here, but it's good to have an understanding of how these two different frequency bands differ from each other. First, the 2.4 gigahertz band, as you all know, has a much greater range. Most vendors are going to advertise about a 300-foot range. That's going to vary quite a bit based on building materials, the access point that you're using, the client devices that you're using, but a 300-foot range is usually the rule of thumb. 5 gigahertz, on the other hand, has a much lower indoor range. It's only got about a 90-foot range indoors. Now, that's great. We've all heard this before. But why? Why do they have different ranges? Well, it's because of the way that different frequencies work. So the 2.4 gigahertz band is, while it's a pretty high frequency, for our purpose here, it's actually a fairly low frequency. So it has a nice long wavelength. The waves are nice and long. They're actually about 4.9 inches from beginning to end. That's about how long a 2.4 gigahertz wavelength is off the top of my head. The 5 gigahertz band, on the other hand, is a much shorter wavelength. Those waves are a lot closer. They're only about 2.5 inches apart, so they're actually a lot closer to each other than in the 2.4 gigahertz band. And because of that, it doesn't go through stuff nearly as well. When it reaches a wall or a chair or anything really, a person, when it reaches an obstacle that it has to go through, it attenuates more. It gets blocked more by objects than the 2.4 gigahertz band does. So as a result, it has a much shorter range. The funny thing is, if you put 2.4 and 5 gigahertz outdoors right next to each other, they have about the same range. It's indoors that 5 gigahertz suffers and has a much shorter range. Now, because of the range issue, 2.4 gigahertz has universal compatibility. Pretty much everything out there supports the 2.4 gigahertz band out of the box, whereas 5 gigahertz still has fairly limited compatibility. Now, a lot more devices, especially with the advent of 802.11ac, which is a 5 gigahertz only standard, lots and lots of consumer devices are now supporting 802.11a, N, and AC, which means we get 5 gigahertz support, which is really, really great. So that's one great thing that AC has done for us, is it's really pushed the adoption of 5 gigahertz in consumer devices. Pretty much every Apple device made these days, with the exception of the Apple Watch, has a 5 gigahertz radio on board, whether it's an iPad, an iPhone, or a MacBook of any. They've all got a 5 gigahertz radio on board. And Apple's been pretty great about putting 5 gigahertz radios in everything for a long time now. Even my old 2009 Mac Mini at home has a 5 gigahertz radio. But you're still going to see a lot of budget Windows laptops, budget Android phones. For example, my Android phone is a budget phone, and it's only got a 2.4 gigahertz radio on board. So watch out for that. There's still lots of devices out there that are 2.4 only. Now, since it's kind of been universally compatible for a long time now, 2.4 is highly congested with Wi-Fi. There's tons of Wi-Fi there because it's the most common place for Wi-Fi. It's just where everything is. And it's also plagued with non-Wi-Fi interference from cordless phones and wireless video cameras and baby monitors and all those different devices. Perhaps the biggest problem with the 2.4 gigahertz band is that it has only 3 channels to work with. We only get 3 channels to use in 2.4, whereas in the 5 gigahertz band, we have 25 non-overlapping channels to work with. You remember how we talked about how only one device can talk on a channel at a time? That means that each channel has a limited capacity on that channel. There's only so much data we can push through a channel. So 5 gigahertz gives us a lot more capacity for a lot more throughput because there's so many more channels to work with. Now, you might be thinking to yourself, Okay, hang on a second, Joel. I've configured a few access points and routers in my day. Pretty sure there's more than 3 channels in the 2.4 gigahertz band. What's going on there? Well, here's what's going on. In the 2.4 gigahertz band, we have about 60 megahertz of space in total to work with. At least in the United States, that's what we get for Wi-Fi. But each Wi-Fi channel is 20 megahertz wide. So you do some math, you go 60 and divide it by 20, you realize that there's only enough room in the 2.4 gigahertz band for 3 channels. So how is it that we have channels 1 through 11 available? Well, it's because of how the channels are laid out. Channels are marked by their center. So for example, here's the center of channel 1. And to find the center of channel 2, we're going to just increment up 5 megahertz. We're just going to go up 5 megahertz, and that's going to put us at the center of channel 2. And when you do that, you realize that channel 1 and channel 2 overlap with each other by about 75%. In the end, the only 3 channels that don't overlap are channels 1, 6, and 11. Those are the 3 non-overlapping channels. Everything else has the potential to overlap with another network. Okay, so the next question you might have is, well, that's great, Joel, but why does it matter if networks partially overlap? Well, it matters because of the different types of interference in Wi-Fi. Now, the main type of interference that you're going to run into probably the most often is co-channel interference. Co-channel interference happens when we've got multiple access points and multiple client devices on the same channel. You remember how we talked about how only one device can talk on a channel at a time. That's what co-channel interference is. Co-channel interference is kind of like a dinner table conversation. When you've got 4 people around a dinner table, everybody gets plenty of time to talk. Everybody gets to participate in the conversation, but they're all going to have to compete for opportunities to talk, right? That's exactly what happens with co-channel interference. The nice thing is that it's controllable, and it's a polite, orderly system. It's a polite conversation that happens. Wi-Fi is meant to do that. The next type of interference is adjacent channel interference. Now, let's say, for example, we've got an access point on channel 5, and we've got an access point on channel 6, and we've got another access point on channel 7. All 3 of those networks and all of the devices connected to them, instead of politely taking turns talking like at a dinner table, they're just going to yell and scream over each other, which is going to cause them to interrupt each other, which is going to cause retransmissions, which is going to make things even busier. Adjacent channel interference is bad, bad, bad. We want to avoid it at all costs, and that's why we always use channels 1, 6, and 11. Now, the type of interference that we're going to be focusing on today is non-Wi-Fi interference. Non-802.11, that means non-Wi-Fi devices, well, they also need time to talk. They need to be able to get on a channel and say what they need to say. The problem with non-Wi-Fi devices is they don't care. They're kind of the honey badger of the world of wireless. They don't care. They don't care if there's anything talking on a channel. So if we've got maybe like an old cordless phone or something like that, it'll just show up on a channel and start spewing garbage all over the channel, which is going to either cause our Wi-Fi devices to back off or cause them to slow down because of the increased background noise, depending on how far away those 2 devices are from each other. So how do we detect interference? Well, there's kind of 2 classic ways of doing that. The first is Wi-Fi scanning. Now, back in the day, there was a great tool called NetStumbler, but it lacked support for 64-bit operating systems, and that's when that was around the time that MetaGeek was just getting started up. And so we said, well, hey, why don't we make a Wi-Fi scanner to replace NetStumbler? And so we did, and we called it Insider. It's kind of a play on the SSID acronym. So Insider is what we came up with. And Insider had this really cool way of displaying networks. Basically, it would scan for wireless networks in the environment, and then it would find out 2 really important pieces of information. The first is, which channel are we on? Are we on channel 1 or are we on channel 6? The second piece of information that it would find is, what's the signal strength of the network? And so are we negative 90 dBm or maybe we negative 70 dBm? So based on the signal strength and the channel, we would plot it out on a graph like this. And that way you could see if anybody was sharing a channel with you, you could see their signal strength, and you could see their if they're overlapping with anybody. And our idea to do this came from our experience from spectrum analysis. And today, this is pretty much the gold standard for how Wi-Fi scanners work. Every Wi-Fi scanner out there now gives you this type of graph. Now, Wi-Fi scanning is really useful because the 2 big things that we can see is what channel are you on and what's your signal strength. So for example, if I was looking at this screenshot here and I wanted to see whether we had a good channel plan or not, I could say, okay, these two APs are sharing a channel, that's okay. These three APs are sharing a channel, that's probably okay. These two are sharing a channel, but what's this guy doing right here? You know, what's MetaGeek Lab doing right here on channel 8? He's causing interference for everybody on channel 6 and everybody on channel 11, and now we can address the problem and we can fix that. But there's some things that you don't get with a Wi-Fi scanner. What we don't get from a Wi-Fi scanner is, well, how busy is channel 1, really? I mean, is it being used 10% of the time? Is it being used 80% of the time? We don't know how busy that channel actually is. Is there any non-Wi-Fi interference up here on channel 11? We don't know. A Wi-Fi adapter can only speak Wi-Fi, and it can't tell us how busy a channel is, and it can't tell us about non-Wi-Fi devices. And that's where spectrum analysis comes in. With a spectrum analyzer, which is a special piece of hardware, in our case, it's the WiSpy DBX, it's going to show you two big things. The first is interference from non-802.11 devices. So if there's a cordless phone ruining your day, you can finally see it. It's not a mystery anymore whether there's something there or not. You can also see channel congestion. How busy is each channel? I mean, how often is channel 11 being used? You can actually see that with a spectrum analyzer. So when I'm troubleshooting Wi-Fi, I always like to start, or actually when I'm doing any troubleshooting with networking at all, I like to start with the physical layer. Now, if I was working with Ethernet, what's the physical layer? The physical layer is copper. It's the copper inside the cables. If I've got a machine that says it's having trouble, if I'm having a machine that's having an issue connecting to the internet, the first thing I'm going to do is I'm going to check the cable. I'm going to see if the cable between the machine and the wall is any good. And if that turns out to be okay, then maybe I'll check to make sure that the cable inside the wall back to the switch is any good. And you could do that in a couple of ways. You could, the low-tech way would just be to replace the cable, swap it out for another cable and see if that fixes it. Or maybe you can use a cable testing tool like a NetScout Link Sprinter is an excellent tool for testing the copper. In the world of Wi-Fi, I'm also going to check the cable. But in this case, it's not physical copper, it's RF, it's radio frequency. And I'm going to check that with the cable tester of Wi-Fi, which is a spectrum analyzer. Now, it's going to show me one of two things. If I fire up my spectrum analyzer and I see something like this, that is a non-Wi-Fi signature. I'm going to go, oh, okay, there's a non-Wi-Fi device here. I'm going to use spectrum analysis to identify and remove that non-Wi-Fi interference. Now, let's say that I see this signature instead. That is the signature that Wi-Fi makes, or one of the signatures that Wi-Fi makes. And I can see that the channel is really, really busy, where the channel is overcrowded. In that case, I'm going to switch to a different tool. I'm going to switch to a packet analyzer, and I'm going to dig deeper into that Wi-Fi congestion to figure out why that channel is so busy. Maybe there's somebody that's talking really slowly on that channel, and I need to go root them out and get that problem fixed. And for packet analysis, I might use a tool like IPA, which is our packet analysis tool that's offered by MetaGeek. But I always like to start with layer 1. I always start with a spectrum analyzer. Now, I don't know about you, but we've been looking at a lot of slides. So I think it's time to go ahead and switch over to a live demo. So let me get this started real quick. We're going to take a look at our environment. We're going to look at what's happening live here at MetaGeek right now. Now, this is what Channelizer looks like. We've got a couple of things plugged in here. We've got a WiSpy DBX plugged in here. It's just a USB spectrum analyzer. I say just a USB spectrum analyzer. It's pretty cool that we can get spectrum analysis from a small USB device. We've also got a Wi-Fi adapter plugged in here. You probably have a Wi-Fi adapter built in on your laptop, so it's no problem. In this case, I'm using a USB Wi-Fi adapter with my MacBook. And we're running this in Windows 10, so it's just normal old Windows 10 inside a virtual machine on my MacBook. So then what we're going to do is the first thing I want to do is I want to explain what is going on in these views. So I'm going to hide the networks for a minute here, and we're going to go one by one and look at these views to help you understand what is actually happening right now. So let's start with this blue line. We've just got the current trace enabled right now. Now this is data coming off of the WiSpy DBX. This is looking at the 2.4 gigahertz band, and this blue line is showing us all of the raw radio frequency activity in our environment right now. So we get a couple of pieces of information from this. First off, where is it happening? On the x-axis, left to right, we can see what channel or what frequency it's on. Now, right now we're looking at Wi-Fi channel numbers, but you can change this to just frequencies in megahertz if you'd like to. The other thing that we can see is amplitude. How loud are things talking? That's on the y-axis here. We can see how loud things are talking. The height of the graph tells us how noisy things are. Now, I don't know about you, but that blue bouncing line, it's kind of hard to see what trends, it's hard to see what's happening over time with that. So I like to enable color by utilization. This is one of my favorite things about Channelizer and the Y-Spy is this view. Color by utilization uses color to show us how often things are talking. So let's take a look at some of these different colors. Let's start with blue. Blue indicates that, whoops, let me switch my pen on real quick here. I always forget to do that. So let's say that we've got a blue spike. Blue indicates that something talked there, but it was 10% of the time or less. So it didn't talk very often. It was just something that showed up really quickly and then was gone. Green indicates about 20% utilization. So something is talking there around 20% of the time. Now, we don't have hardly any yellow at all. There's just a little tiny bit down here. Yellow indicates 40% utilization or more. And red indicates there's just a little bit of red down here at the bottom. That's just the background noise in our environment. Red is 50% utilization or more. Basically, the color tells us how often things are talking. So if you see a blue spike, that's kind of like a clap. Listen to a clap. Did that really interrupt our conversation? No, not really. There was a clap, it was here, it was gone, and then we picked right back up where we were and kept on going. Whereas red indicates constant activity, kind of like an air horn. If somebody opened the door into our little studio here at MetaGeek where I'm giving this webinar and blasted off an air horn, maybe just held the button down on the air horn until it emptied the entire can, that would definitely interrupt our conversation, right? Fingers crossed it hasn't happened yet during a webinar, so that's good, I suppose. But that would completely interrupt our conversation. In this environment, an air horn would essentially be colored red. Something that talks constantly like an air horn would be colored in red. Okay, so let's clear all this stuff off of the screen. And the next thing I want to show you is the built-in Wi-Fi scanning. Now, if you've used Insider or if you've used any Wi-Fi scanner out there, this is going to be pretty familiar. We can actually scan for wireless networks with our Wi-Fi adapter. So what I'm going to do is I'm going to come down here to the networks table. And I'm going to apply a filter here. I'm only concerned about the MetaGeek access points here. So I'm just going to filter down to MetaGeek. We've got a couple of here. We've got one that I've labeled reception and one that I've labeled meeting room. You can actually label these in Channelizer so you can figure out which access point is which much more easily. So now we know where our access points are. We know what channels they're on. So now let's have some fun. I'm going to introduce a non-Wi-Fi device here. So I just turned on a non-Wi-Fi device, and it's not going to take you very long to figure out where it is. If you look right centered on channel 4 between channels 3 and 4, you'll notice a spike that showed up. It's pretty tall, so it's pretty loud. And we can see in the waterfall view down below, we can see where this device started to talk. Now, in the waterfall view, color does not indicate how often something is talking. Color indicates how loud it is. So you'll notice that the tallest point of this signature directly correlates to this red stripe. So red means loud, blue means quiet, and black pretty much means nothing. It means there's nothing going on there. So we can see that there is something talking. In fact, it's talking so loudly, we can't even hear our access point that was called reception. It's gone. We can't even hear that device anymore. It is no longer transmitting. So now let's say that we need to figure out what this device is. I'm going to go over to the interferers tab, and this is a library of common shapes or common signatures in the spectrum. Now, what we can do is we can kind of compare this to see if it matches up with what we are seeing in the spectrum. So if we go through here, we could say, is that a Nortec video device? We can click on it and we can hover our mouse up here to see if it matches up. And in this case, I'm going to say, no, that's definitely not a Nortec video device. It's also not an AV transmitter. It just doesn't match up. But it kind of does look like this. It kind of does look like this Uniden phone. So if I hover my mouse up there, we can see that matches up pretty well. It's got that little bump on the side right here. That really does look like that might be a Uniden phone. So now we know, okay, we know what we're looking for. This looks like a Uniden cordless phone. So what I'm going to do now is we're going to physically track this down with the device finder mode. So what I'm going to do is I'm going to click and drag, and when I release my mouse button, I'm going to click on device finder. And I can clean up my selection just a little bit. We'll tighten it up just a touch here, and then we'll hit the checkbox to start device finder mode. Now in device finder mode, we give you this signal strength graph for this device. If we move away from that device, we're going to see the signal strength go down. And if we move toward that device again, we're going to see the signal strength go up until pretty soon the signal strength maxes out because we're standing in the same room as the device that we're looking for. And that's when you can start visually trying to identify it. And as soon as you find it and turn it off or unplug it or whatever you need to do, you'll see the signal strength fall to the floor because that device is no longer transmitting. Now, obviously, I'm sitting at a desk. I'm not actually moving around, but you can see how the signal strength goes up or down depending on how good the signal is from that device. So that's how you can track something down and actually get rid of it. One more thing I wanted to point out about this cordless phone, if we power it on and let it show up somewhere, notice that this time it shows a frequency up above Wi-Fi channel 13. Every time I hit the talk button on this phone, end the call, and then hit talk again, this phone has a good chance it'll actually switch to a different frequency band. So you can see here in the waterfall view where it begun transmitting right there. It transmitted for just a few seconds, and then it stopped. If I turn it back on, you can hear the beep there as I hit the talk button. Now you can see it show up down here between channel 3 and channel 4. This is bad. This is really, really bad because this device likes to pick a different frequency whenever you power it on or off. It's not going to stay put, so it's going to be really hard to plan your wireless network around this device in the 2.4 gigahertz band. That's going to be really tricky. So we talked about the waterfall view down here, how it shows amplitude. It shows it in a rolling time span. It shows it over time. So here's what's happening right now, and down here at the bottom, this is what happened 30 seconds ago. You may have noticed that there's an identical waterfall view over here on the left-hand side. This waterfall view, it's the exact same thing, but instead of showing us a 30-second rolling time span, it shows us the entire recording session from start to finish. So there's some cool things that we can do here. For example, we can hit the pause button, and it's going to pause everything that's happening in the application. We've paused everything about what's happening, except the waterfall view over here is still recording in the background. These two navigation playheads, the two yellow ones here, that is showing us what we have displayed in the rest of the application right now. So for example, we can click and drag to rewind. So now we have just rewound to when the cordless phone was up here on channel, up here above channel 13. We can scroll it back up to look at when it decided to come back down here to channel 3 and channel 4. And you'll notice I just turned off my cordless phone. You probably heard it beep again when I hit the end button. You can see where the cordless phone stopped talking right there. And we can bring this back up to live. Now we're looking at live data. So this works just like a DVR. It's just like a TiVo, except for instead of movies and TV shows, we're just looking at spectrum. We can also change the time span that we want to look at. So for example, if I bring this back down, our time span is currently set to 30 seconds. If I hit the plus button, we can bump it up to a minute. You'll notice that all this data got a little less granular, and it's got a little fuzzier because we've crammed more of it into the spectrum. I can even set a completely custom time span. We can set the bottom here, and we can set the top one. We can set the top one right here. We have now selected 14 seconds worth of data. We've selected a very exact time span. But I'm going to go ahead and bump it back up to 30 seconds, and I'm going to jump to our live data so that we're looking live in our environment right now. Okay, so the next thing I want to do is we've looked at non-Wi-Fi. Let's take a look at what Wi-Fi looks like. I've got an Android tablet here on my desk, and I'm going to go ahead and I'm going to run a throughput test with this Android tablet. Now this thing's down in 2.4 gigahertz, so we're going to see it quite clearly here. You can see in the waterfall view that something started to talk right there, and now we can see this flat tabletop shape emerging on channel 6 right within the confines of where the quote-unquote meeting room access point is. Okay, so we can clearly see that is our Wi-Fi throughput test. To be specific, if you're wondering what hardware I'm using, I've got a good old 2012 Nexus 7 here, and I'm running an iPerf to a Raspberry Pi 3 server that I've got connected via Ethernet on our network. It's not very fast for a throughput testing machine, but it's fast enough to show what's going on here. Now you'll notice that during this transmission, you can see where we started. Let's grab a little bit more time here. You can see where we started and where we ended. And if we focus down on this event a little bit more and we look at the shape here, notice that shape there is dark red, which means it's talking at least 50% of the time. If we want to know exactly on a percentage basis how often the channel is being used, I can go over here to the channels table and take a look at channel 6, and you can see that our utilization on this channel is 66%. So the channel isn't completely slammed, but it's getting close. Once you hit about 70 to 80% utilization, that's when you're going to start seeing a pretty severe degradation of performance on that channel. That channel's not going to perform very well. Just for fun, let's go ahead and run one more. We'll kick off our throughput test one more time, and you can see where that throughput test immediately begins. So that's what Wi-Fi looks like. If you've ever wondered what it actually looks like in an environment, that's what to look for. That's what Wi-Fi actually looks like in the environment. Now, we didn't spend any time in the 5 gigahertz band today, but I just wanted to give you a quick look. Of course, the Wi-Fi does. The Wi-Fi DBX is capable of looking at the 5 gigahertz band. There are actually quite a few networks here. If we get rid of our MetaGeek filter here, we can see where all of those networks are. But 5 gigahertz, especially here at MetaGeek, is reasonably quiet. It's actually a fairly quiet place to be. If we zoom in, let's zoom in down here on our lower uni channels here. You can see that we're using 20 megahertz wide channels. We've got one of ours is on channel 40. The other one that we can see from here is on channel 44. And we've got a neighbor who's got his SSID hidden. We can still see it, the network's there. We just don't know what the SSID is. And if we look at our utilization, channel 48 is only being used about 1.8% of the time. So that's just a great example of how quiet and serene 5 gigahertz usually is. Not always. Some environments it can be pretty nuts. So I want to take you through some common shapes, some common signatures of different things that you might see in the spectrum before we open up for questions. This is what 802.11b traffic looks like. It'll make a curve shape in the spectrum with these lobes down each side. Now, when we see this shape, this means that we're using an older, slower data rate. This modulation scheme, that's basically the language that these devices use, is called direct sequence spread spectrum, or DSSS. That means that we're using a data rate of 1 or 2 or 5.5 or 11 megabits per second. And that could be an indication that things aren't going so well. If you are seeing curve shapes, the first question I'd be asking is why? Why are we seeing curve shapes? That means that a client device is really far away from the access point, so it's had to fall all the way back down to these original 802.11 and 802.11b data rates, or there might just be an 802.11b device on your network talking slowly, eating up all of your airtime. This is what 802.11g and 802.11n look like. They use a swankier, faster, newer modulation scheme called OFDM. Oh, I should not have committed to drawing this on the screen. OFDM stands for orthogonal frequency division multiplexing, and it makes this flat tabletop shape in the spectrum instead of the round shape. This means that we're using a faster data rate. That means we're using a faster data rate like 6 or 9 or 12 or 18, 24, 48 or 54 megabits per second and beyond. This means that we're using a faster, newer data rate. And so it's much more common these days to see a flat tabletop shape. Now, we didn't see a lot of activity in the 5 gigahertz band when we went and checked it out, but 802.11a and 802.11n make these 20 megahertz wide channels in the 5 gigahertz band. Now, don't be deceived here. The 2.4 gigahertz band, by comparison, is only this big. That's how big 2.4 is by comparison. These are still 20 megahertz wide, just like in the 2.4 gigahertz band. We just have to squish it all down to fit it on the screen here. So that's why it looks a lot narrower. It's actually the same width. This is what a baby monitor looks like. This is a really frustrating one because it likes to frequency hop, just like our cordless phone did, except this frequency hops just on a regular timed basis. So if we look at this slice of time here, we can see that this baby monitor started out right here on channel 5, and it hung out there for about 4 seconds or so, and then it moved all the way up here to channel 9. So here it is right here on channel 9. It hung out for another 4 seconds or so, and then it moved down here to channel 1. And when it moved down to channel 1, it did something really, really nasty. Because if you look closely, you'll notice that there's a flat tabletop shape right here on channel 1. That is an 802.11g network. So this baby monitor chose the same channel as an 802.11g or 802.11n network, which means it's going to completely interrupt communications on that channel. So for the end user here, the Wi-Fi will work, and then it won't work, and then it will work, and then it won't work, and that's going to be a really frustrating end user experience. This is another form of frequency hopping, but this is a fast frequency hopping device. This is what Bluetooth looks like. Now, don't be confused. It's not called Bluetooth because it has blue teeth. It just so happens, it's just a coincidence that it looks like blue teeth on our spectrum analyzer, which I think is pretty cool. Bluetooth rapidly hops from channel to channel to channel. When you pair a couple of Bluetooth devices together, they pick basically a random set of channels, a pattern of random channels, and they rapidly hop from channel to channel to channel. They only dwell on each channel for about 1 millisecond. They don't spend a whole lot of time on each channel. And so notice the utilization here. It's blue, which means it's talking less than 10% of the time. At these lower amplitudes, we start to see around 15, maybe 20% utilization. But this is also the exception. This is a Bluetooth device that we are keeping very, very, very busy. During this entire webinar, I've got a number of Bluetooth devices around me. I've got a Bluetooth mouse, which I've been using the whole time, a Bluetooth keyboard. My phone's got Bluetooth enabled. My Pebble smartwatch has Bluetooth enabled. We never even saw it on the spectrum analyzer. Bluetooth just does not talk that often. It's not an air horn, it's a bunch of little claps, so it doesn't cause a significant amount of utilization. Same idea, but not the same protocol, are Xbox 360 controllers. They're also frequency hopping, but again, look at the utilization. Each one of these spikes is a hop from an Xbox 360 controller. They're almost barely detectable. It's very, very hard to even see these because they just don't talk very often. Unless you have a couple hundred Xbox 360s in one place, it's not going to be a problem. You're not going to have any issues. These are wireless microphones with a little bit of Wi-Fi thrown in the middle. So these microphones are taking out channel 1 pretty hard, but fortunately they're not affecting channel 6 or channel 11, so we're actually able to plan around those microphones a little bit. We can make sure that our access points are on good channels to avoid those microphones. And this is an old X10 wireless video camera. These are very, very nasty because look at the utilization. This is dark red, which means it is talking constantly. These analog video cameras make a very distinct 3-spike shape in the spectrum, a very, very distinct shape, but these will wreck your wireless networks. You want to avoid those at all costs. All right, at this time, I'd like to go ahead and hand it back over to Julie for any questions. So, Julie?
Thank you, Joel, very much for that wonderful presentation. We enjoyed it very much, and I do have some questions for you. Let's go ahead and start off with the first one here. Does MetaGeek have any plans on branching into making access points with their spectrum analyzers built in?
Ooh, that's a great question. We don't have any plans to make access points because we're a tools vendor, and there's lots of great vendors out there that already offer excellent access points. Talk to Microcom. They've got lots of options available. As far as getting spectrum out of an access point, though, right now we integrate with Cisco. We can connect to a Cisco Clean Air access point, and we can pull spectrum down from an access point. So as the technical trainer at the company, I've always dreamed of being able to connect to any vendor out there and pull spectrum analysis data down from the access point. But currently, Cisco is the only access point vendor that's approached us and asked us to integrate with their onboard spectrum analyzer. So at this time, only Cisco Clean Air access points. But I am hopeful. I would love to see integrations in the future.
Thank you very much for that, Joel. Let me go on to the next question. Can you tell us about where MetaGeek products are manufactured?
Yes. So all of the software development is done here in-house in our office in downtown Boise, Idaho. You might have to Google Boise, Idaho to know exactly where we are. We're in the Pacific Northwest. All the hardware is also manufactured here in Boise. We contract out to a hardware manufacturing company that's just a couple of miles away, and all Wi-Fi devices and device finder antennas, everything is all made right here in Idaho with real 100% Idaho-grown potatoes.
Fantastic. Thank you. Got another question here for you. Is there support available to assist in early usage for reading the data we analyzed?
Yes, absolutely. We always help customers analyze recordings. One thing I didn't show you is you can save a recording file off of Channelizer and play it back later. It's called a .wsx file. The files are usually very, very small in size, usually 1 or 2 megabytes tops. Once I saw one that was like 90 megabytes, and it was days long. It was tons and tons of time. If you contact our support team at support@metageek.net or by opening a ticket on our website, those both go to the same place. We've got a wonderful support team here. Both Casey and Christina are really good at looking at those recordings, and they would be more than happy to take a look at those recordings and kind of help you get familiar with how to read those recordings before eventually just turning you loose to let you do it on your own. But in a training capacity, we're more than happy to look at recordings for you.
Thank you, Joel. In addition to that type of training, however, do you have online courses available?
We don't have courses available yet, something we'd really like to put together. But what we do have is on our knowledge base, we've got tons of how-to articles for how to use all the different various aspects of Channelizer and the WiSpy. So each view, each type of view is broken down in detail. And so if you go to our knowledge base, just go to our website and click on the links to go to our knowledge base. Then there's lots and lots of articles there. You could spend a lot of time in there learning all the intricacies of our software. We hope to put together a step-by-step course in the future, but it just hasn't quite happened yet.
Thank you, Joel. Is there any possibility at all that perhaps Microcom could assist MetaGeek in building these courses, putting them together?
That may be something we'd have to talk about.
Excellent. I think I have one last question here for you. Are there any licensing requirements for the Channelizer?
Yes. So when you buy the product from Microcom, you're going to get both a hardware and a software bundle. They come together. You can buy the software separately if you'd like to. Basically, the license is good for one user on multiple machines. So you want to buy a license per user. But if you're anything like me, I've got a couple of different laptops. I've got a couple of virtual machines. I need to be able to activate the software on multiple machines, and we recognize that. So we allow up to 5 activations per user. And you can manage those activations. You can deactivate your own machines if you'd like to activate a license key on a newer machine. So it's one license key is good for one user on up to 5 machines.
Excellent. Thank you very much for answering those questions, Joel. And thanks for everyone for attending today. If you have any other questions, please feel free to contact your sales rep, or you can email us at sales@microcomtech.com. And if you wish to view any of the products mentioned or shown here today, please visit our website at www.microcom.us. Also, please remember this webinar presentation has been recorded and it will be uploaded to our Microcom YouTube channel. So if you'd like to view it again, you can certainly do that. Thank you again, Joel. Appreciate your time and your presentation today. And everyone have a wonderful, fantastic day.